Swayam Prabha. Digital India. Educated India.
So far we have seen how to design or how to calculate the strength of a bolt if it is subjected to shear force and if it is of bearing in nature. So these are the three cases where bearing type connections or a bolt which is in bearing type bolt, when it is subjected to shear force, how to calculate its strength. And we have considered the shear strength, bearing strength, and including the correction factors which correspond to extra long bolt or extra long joint, or the case where there is a packing plate, extra thick packing plate. Now we will talk about the bolts which are not bearing type connections, but they are a part of friction grip type connection, where the bolts are held in place or the plates are held in place through friction. And such plates have to be designed to resist slip between the plates, or such connections are designed to resist the slip. And the limit state, corresponding limit state, is the slip failure. So we will talk about how to design under such conditions. So since we know that it is the plates are held in place through friction, the strength of that connection would be basically a function of the friction force. So the slip resistance of the bolt will basically control the strength of the connection. So a single bolt would have a strength which is basically equal to the slip resistance of the bolt. That again can be calculated as the friction coefficient between the plates multiplied by NE, and E here corresponds to the number of interfaces which are offering the friction. KH is a coefficient which is represents the situation when the holes are slightly larger than clearance holes. So if the hole size is greater than the clearance hole size, then the KH is reduced. Otherwise, for standard clearance holes, KH remains 1. And F0 here corresponds to the bolt, the amount of tension that is present in the bolt. Because the amount of tension that is present in the bolt, that is proof stress level load, that would be same as the compressive force between the plates which are trying to slip, right? So essentially, if you see this formula is nothing but friction coefficient multiplied by the normal force. So F0 corresponds to the normal force and friction coefficient is the friction coefficient, which will be the slip force or sliding force. Okay. For example, if I have this lap joint that we have seen before as well, and there is a bolt which is connecting these three plates together and it is pre-tensioned, then for this plate, the middle plate, to be able to slip out, we need to overcome friction at these two interfaces, at these two planes, right? So there are two such planes where the friction is acting. And why is that friction present there? The friction is present because of the tension in the bolt. There is a compression between these two plates. So between this plate and this plate, there is a compressive force which is holding the bolt in place. Likewise, there is a compression between this plate and this plate, right? And because of the presence of this compression, that normal stress, there will be a shear slip resistance that will be present. So in this particular case, for example, we would have NE equals to 2. All right. Now that VNSF, which is given here, is basically the nominal strength. There is no factor of safety applied yet. After applying the material factor of safety, we would use gamma MF value, which is the material factor of safety, which is either 1.1 or 1.25 depending on the following condition. If this joint is supposed to behave like a slip critical joint under ultimate conditions also, that is under ultimate loads also, then the factor of safety is to be taken as 1.25. But there are situations when many times these connections are designed to be slip critical under service loads, that is under serviceability conditions, but they are designed to be bearing type connections under ultimate load conditions. So basically we don't have to apply enough tension force so that it can resist through friction the entire maximum load. Through friction it has to only resist the service loads, so that from day to day requirement there is no slip. But however, whenever there is a ultimate load, the maximum possible load that comes to the structure, at that time it allows for the slip, and then the connection changes its behavior into a bearing type behavior. So if that is the design philosophy, then for service load conditions, that is for slip resistance, we will take a factor of only 1.1. The friction coefficient that we just saw, we can get the values of friction coefficient from table 20. This is again clause 10.4.3 of IS 800. The values of friction coefficient between the two steel plates can vary between 0.1 and 0.52. So this is a wide range, and of course it depends on the surface treatment that is provided between the two plates. So if the two plates are treated with a smooth finish, what could be an example of a smooth finish? If it is a red lead paint surface, or if it is a galvanized surface, then the friction coefficient will be very small and we can take a friction coefficient of only up to 0.1. However, if the surface is sandblasted and sandblasted followed by some rusting, in such situations we can see that friction coefficients of up to 0.52 can be taken, which will basically a very rough surface, and that will increase the slip resistance. So these coefficients can be taken from this table. Now, just to reiterate, the two different factors of safety, material factors of safety, for service load conditions, if it is slip critical, we will be taking 1.1. But for ultimate conditions, under that is strength limit state, if we want the connection to behave as a slip critical connection, then the factor of safety will be taken as 1.25. Now, in such a situation where the connection is assumed to be slip critical only for service conditions, for ultimate loads, we would design the connection just like we did design the bearing type connection. So the shear strength in that case will be similar to this, and a factor of safety of 1.25 will be applied, and the bearing strength will be again given by the same expression that we have seen before. This corresponds to bearing failure of the bolt, bearing failure of the plate, bearing failure of the plate if the hole is very close to the edge, and bearing failure of the plate if the holes are too close together in the direction of the load. So the same limit states that we have seen before for bearing strength, the same limit states would apply. Only thing is, just like before, the factor of safety will be taken as, material factor of safety will be taken as 1.25 in this case too. So now so far we have discussed all the possibilities when the bolted joint is subjected to shear. The bolted joint could be of bearing type or it could be a friction grip type. Now we will talk about the situations when a bolted joint is subjected to tension. What could be such a situation? A common situation could be when I have a plate, and to this plate I attach a T section, and this T section is basically supporting some load, and this T section is bolted to the other plate using these two bolts. So these two bolts in this situation would be under tension. So what would be the design strength of such bolts when they are subjected to tension? We will discuss that. Then at the end we will discuss the situation when the bolts are subjected to a combination of shear and tension. Before we go into the details of the design provision, you might recall from the basics of hello. Haan, Papa. So now before I go into the details of how these bolts are to be designed in tension, let me try to recall some discussion that some basic concepts that you might have learned while learning the design of steel members in tension. So you might recall that when we have a steel plate that is subjected to tension, if it has a uniform cross section like the one that is shown here, the strength of this plate in tension is given by cross section area multiplied by Fy divided by gamma m0. Right? So area was the cross section area, Fy was the yield stress of the plate, and gamma m0 was the factor of safety for yielding, which had a value of 1.1. However, when this plate had a non-uniform cross section, let's say there was a hole in the plate somewhere, and then the cross section area here is different from the cross section area here. In such a case, the tensile strength of this plate was actually equal to, was governed by whichever section had lower strength. So the gross cross section, this cross section was called a gross cross section, and this cross section was called a net cross section. Net cross section is susceptible to rupture. We did not worry about net cross section yielding, because when we confine the failure, the governing limit state becomes the rupture limit state, and then we take the net cross section area. So the strength was basically equal to minimum of Ag, gross cross section area, multiplied by Fy gamma divided by gamma m0, that was 1, and the other value, that was An, net cross section, multiplied by Fu divided by gamma m1, and then there was an additional factor of 0.9 that was applied to account for the significant consequences of a rupture type of a failure. You might recall that, right? So here there are fundamental differences. One was that An was taken instead of Ag, Fu, ultimate stress, was taken instead of Fy, right? Because when we talk about net cross section, we talk about rupture failure. We don't mind if a net cross section, that is a localized cross section, if it has some localized yielding, that is not a problem, that we tolerate. But we don't worry about it yielding there. We say only when a localized cross section starts to rupture, that's when the strength limit state is reached. Gamma m1 is basically provided as an additional factor of safety, which has a higher value than gamma m0. Generally it was taken as 1.25, and then an additional factor of safety of 0.9 was used. Exactly the same concept can be utilized while designing a bolt in tension. So when we see a bolt that is subjected to tension, you can imagine that this is a bolt, and then there is a nut here which is basically pulling the bolt to this side at this end, and it is being pulled to this side at this end, right? As a result, this portion of the bolt is subjected to pure tension. Now this much part of the bolt is having a uniform cross section which is larger than the portion that is here. So this portion has a net cross section which we call A net, and the strength or the failure in the net cross section area will be a rupture type of a failure, and we will use the limit state of Fu, that is ultimate stress, multiplied by the net cross section divided by gamma mb, which has a slightly higher value than gamma m0, and an additional factor of 0.9 because we want to avoid rupture and we prefer to have a failure governed by yielding. The other limit state is Fyb, which is yield stress, multiplied by Asb, which is the entire cross section area, gross cross section area of the shank, and divided by gamma m0, which has a smaller value. That means the factor of safety is smaller, 1.1, whereas this value is 1.25. So the concept wise, it is the bolt in tension has very similar limit states as a plate in tension. Now, as we already know, Fu value, for example, if I have a bolt of grade 8.8, then Fu value will be 800, and Fy value for this bolt will be approximately 640 MPa, right? Similarly, An and As, the relationship between An and As is An is approximately 78% of As, shank area. So with these two relationships we already know. We know the values of gamma mb and gamma m0. So by using these values we can calculate the tensile strength of a bolt. Whenever the bolts are subjected to tension, there is a phenomenon which is known as prying action. P-R-Y-I-N-G. You might notice it here. That's a very interesting phenomenon, and let's talk about that for a minute. This happens only when the bolts are subjected to tension. It does not happen when the bolts are subjected to shear type of force. So let's take a situation. Let's say these are the two T sections. One T section is this one, and the other T section is this one. These were straight in the beginning, and then they are being pulled in two different directions as shown here. And they are held together with the help of two bolts. Both of them are marked here, bolt 1, bolt 2. Now you might appreciate that the bolt cannot be placed at the very edge. It has to be slightly inside. And if the plates themselves are not perfectly rigid, they are slightly flexible, which they are most of the times. So if this plate is flexible and the bolt itself is also slightly flexible, when these plates pull apart, they undergo a curvature, and as a result, the farthest end of these plates or these flanges start to bear against each other, right? And that additional bearing, if you draw the free body diagram of this plate, you would see that that additional bearing is actually an additional force that is acting on this plate, which has to be resisted by the bolt. So if there was no prying action, we would assume that if T force is applied here, so each bolt would resist a force of T divided by 2 if it's a symmetric system, right? However, because of the prying action, let me draw the free body diagram of this one of the T sections. If this force is T and there is a prying action, let's say that force is Q, then similarly there is a Q force here. At both ends you have a prying force of Q, which is basically coming through the bearing with the other plate. Now as a result, the only way this T section can be in equilibrium is if the bolt resists a force of T divided by 2 plus Q, right? So now you can see that in comparison to the situation where there was no prying action, now we have got an additional force of Q in the bolt. That is an unintuitive, non-intuitive kind of a situation which has to be accounted for when we are designing a bolt in tension. There are a lot of researchers who have looked into this behavior of plate sections or plates which are subjected to this kind of a tension, and the bolts, how the force increases for the bolt. There are several equations which have been proposed in the literature. The Indian code has adopted the equation which was proposed by Owens and Cheel in 1989. The equation for this Q force, Q is the additional tension force in the bolt, is given by this expression. This is primarily an empirical equation wherein some of the factors that are listed here, you can see LV is the distance from the toe of the weld to the center of the bolt, right? So that is basically kind of a lever arm on this side. LE is the lever arm. This is the LE value. LE is the lever arm on the other side. TE was the original tension force which was acting on a single bolt, that TE. Beta is a factor which depends on whether the bolts are pre-tensioned or not. So if the bolts are pre-tensioned, beta can be taken as 2. If the bolts are non-pre-tensioned, beta can be taken as 2. If the bolt is pre-tensioned, beta will be taken as 1. Another factor, eta, it has a constant value of 1.5. F0 is the proof stress, the level of proof stress in the bolt. So we know the proof stress is typically taken as 70% of Fu value. So that's what F0 will be. Be is the depth or width of this plate in the perpendicular direction. That is the width that is corresponding or to the one row of bolt. So this is one row of bolt. So how much of the width of this section is supported by one bolt? That is the width, Be. T is the thickness of this plate, because how much prying action will develop also depends on the plate thickness. If the plate is very, very thick, it does not deform at all, and as a result, there won't be much of a prying action. So T has an important role to play there. Divided by 27 LE/LV, which we have seen already, which factors these are. Okay, so we can use this expression to calculate the additional tension force demand in the bolt. So now let's do one example. So let us try to solve this example. This plate is held in place. So the thickness of this plate and properties of this plate don't really matter. This particular plate is tied to the first plate using these two bolts. The bolt properties are given. The diameter is 24 millimeter and material is 8.8 grade bolt. This plate, the second plate, its dimensions are 250 millimeter width in this direction. The depth is 150 millimeters. So that 150 millimeter depth is supported by these two bolts and thickness is 35 millimeters. The plate is made of E250 steel. So it has a yield stress of 250 MPa and ultimate stress of 410 MPa. Also, this web is welded to the plate, to the flange, using two 8 millimeter fillet beds as shown here. Okay. The other dimensions, for example, the edge distance here is marked as 40 millimeters. Right? So, the bolt is given as a pre-tension bolt. So some of the factors in that equation will be affected by that. Now we remember, let me copy paste that formula for the capacity of the prying force. Now in this expression you might see Q is the additional force. So each bolt is likely to have will be equal to 150 kilonewton divided by 2 plus the Q force. So we need to calculate what is the Q value, right? Q value will be given by LV divided by 2LE. TE is actually the force in each bolt without accounting for the prying action, minus beta eta F0 BE T to the power 4 divided by 27 LE LV squared. Let's try to calculate the values of each of these factors. F0 here is the proof stress level, which is generally taken as 70% of the ultimate stress. The ultimate stress of the bolt is 800. Therefore, we will take it as 560 MPa. Beta, since this is a pre-tension bolt, beta will be taken as 1.0. If it were not a pre-tension bolt, beta would have been 2.0. Eta is a constant with a value of 1.5. BE is the depth in this other direction. That depth is equal to 150 millimeter. LE we need to calculate. So LE is actually given as minimum of the edge distance, that is distance from the center of the bolt to the edge, which in our case is 40. And there is another small expression which was mentioned there in the previous slide, 1.1 times T multiplied by square root of beta F0 divided by Fy. So this Fy is Fy of the plate, by the way. So let's try to calculate it. (1.1) multiplied by thickness of the plate. The plate has a thickness of 35 millimeter. Square root of beta is again 1.0. FO is 560. And the yield stress of the plate is 250. This value turns out to be 40 millimeters because the value on the right hand side is actually equal to 57.6 millimeter. So the minimum of the two will be 40 millimeters. So LE is 40. LV is relatively straightforward in comparison to LE. LV is the distance from the edge of the fillet to the center of the bolt. So which is easy to calculate. We know the distance from the center of this plate to the center of the bolt. The total distance was 250. Half of that is 125. This distance is 40. That means this distance is also 40. So LV will be equal to 125 minus 40. So this part is gone, minus 8. Minus the half of this thickness, 10, which will be equal to 67 millimeters. Now we know all the components of Q. So Q value can be calculated as, we can substitute all these values here in this expression. Actually, I'm not going to substitute them again, which basically turns out to be, we have to be mindful because TE we have to put in newtons. So the TE value that is given to us is 75 kilonewton. So we will put 75,000, and basically this turns out to be 67 divided by 80, 75,000 minus, I believe, 39,000. And this turns out to be 30.15 kilonewton. So you might realize original force without the prying action was 75 kilonewton. Now that force has increased by 30.15 kilonewton. As a result, total tension force demand on the bolt (75 plus 30.15), which turns out to be 105.15 kilonewton. This is the total force demand on the bolt. So we have seen that when the bolts are subjected to tension, they have a strength which is governed by the yield of the shank cross section or the rupture of the net cross section. Right? So this was the expression. Now it is worth it to notice that this expression remains the same even for the bolts which are pre-tensioned. So other than the prying action effect, which depends on whether the bolt is in pre-tension or not, the tensile strength of a bolt does not really depend on whether the bolt is subjected to a pre-tension or not. So the tension capacity of a friction grip type bolt which is in pre-tension, it remains the same. It is given by the same expression. And this is a rather counterintuitive proposition. As we might understand that when the bolt is subjected to an external tension force demand, even before that, a pre-tension bolt is already at a very high level of tensile stress, which is usually approximately 70% of its total strength. So a bolt which is under that high a tensile stress already, when we apply an external stress to it, how can it still resist the entire bolt strength which was available if the bolt were not in pre-tension? The same strength or same amount of external force it can resist still. How is that possible? That is a very counterintuitive kind of phenomenon, and it is explained very nicely in the book that is one of the reference books that I have mentioned in the beginning of this course, by Selman Johnson's book. So I strongly recommend you to read that part. I'm not going to be able to explain that in this course, but it is recommended that you read through that material and develop an understanding of why is that the case. So, so far we have discussed the shear behavior, tensile behavior for both a bearing type of bolts and friction grip type of bolts. Now we will go into the behavior of bolts which are subjected to a combination of shear and tension. So as you might see in this diagram, these bolts are likely to be subjected to a combination of shear force because of this force. Direct effect of this force will be a shear force demand on these bolts, and a combination, and as a result of this moment, there will be tension force demand in the top bolt, and there will be some kind of a reduced tension force demand in the bottom bolt, most probably, if there is any uh, if there is a contact between the bottom flange and the column. If there is no contact, there may even be some bearing resistance coming from here. Anyway, for such type of bolts which are subjected to a combination of shear and tension force demand, there is an interaction curve. This interaction curve basically has an elliptical shape, which is given by this equation. So essentially, this expression tells us that we will calculate the shear force demand, which is given by VSB. Okay, this is factored shear force demand, and shear capacity, which is given by V sub dB. Likewise, we calculate the tension force demand and tension capacity individually. So this tension capacity is calculated as if there is no shear force acting on the bolt, and the shear capacity is calculated as if there is no tension acting on the bolt. And then for the and by the way, these capacities already include the material factors of safety. So that's why these are design strengths. Then in this interaction equation, we take the division and then we square it, both terms, and that final value should be, the summation of the two should be less than or equal to 1. This is an interaction equation. If I plot it on a plane which represents shear force on horizontal, which represents tension force in the horizontal axis and shear force demand in the vertical axis, and let's say this is the shear demand capacity or shear capacity, and this is the tension capacity of a bolt, then the interaction curve will be looking like this. Everything under or inside this ellipse will be safe. At the boundary, the the limit state of strength under a combined tension and shear condition is reached. So that is this equation. This equation can be used to calculate the combined tension and shear capacity of a bolt.